Hello guys, today you're going to learn the first well logging tool, that is spontaneous potential log or SP log. As I mentioned before, well logging is an important step in formation evaluation, and here in this course you're going to learn 7 well logging tools that are used in formation evaluation. So what is well logging? As I mentioned before, well logging is that we have different sensors, and each of these sensors measures a specific physical or petrophysical properties. And by integrating different data that we get from these sensors, we are able to have some quantitative evaluation of a formation. And these sensors are called SONDs, or SONDES. The first well logging was conducted in 1927 in France by Schlumberger brother. They measured the resistivity of subsurface, and now we know that Schlumberger is one of the major service companies in oil and gas industry. They provide so many services for oil and gas companies, and also they have developed so many applications that are used for hydrocarbon exploration and also production. As I mentioned before, well logging is indeed we send some zones into the borehole at the bottom of the borehole by a cable, and then gradually bring them up to the surface. At the same time, these zones measure different physical or petrophysical properties. Here, as you see, there is a link of YouTube video, and I encourage you to watch this video. It is very insightful and gives you a better idea about the entire well logging operation. As you see here, you're going to learn 7 different well logging tools. The first 2 well logging tools, spontaneous potential and gamma ray logs, are used to identify permeable from impermeable layers. And then you're going to learn about electrical resistivity, that is used to first identify hydrocarbon saturated layers. Then we can measure 4 important resistivities: RW, RT, RMF, and RXO using uh, the resistivity log, from which we can estimate SW, water saturation in the virgin zone, and SXO, water saturation in the flush zone. And we know that these two saturations, from these two saturations, we are able to estimate, first of all, the uh, hydrocarbon saturation in the formation, and also we may have some rough idea about the volume of the producible hydrocarbon in the formation. And then, as you see here, we're going to have neutron porosity log, density log, sonic logs, and also nuclear magnetic resonance, or NMR. All of these 4 logging tools are used to estimate porosity. And the reason why different logs have been developed to estimate porosity is that each of these logging tools measures the porosity with respect to a specific physical property. And this is how, if we combine different logging tool, for example, neutron porosity log and density log, if we combine their data, we can have a more accurate estimate of the porosity. Or sonic log helps us to estimate the primary porosity, from which we are able to estimate the secondary porosity. And NMR logging tool is relatively new logging tool that not only measures the porosity but also other petrophysical properties such as permeability. And this one also is the most expensive logging tool. Okay, now let's go and learn about the spontaneous potential and how it works. As you see here, a spontaneous potential, the principle is very simple. So what we have 2 electrodes. One of them is fixed on the surface, and The other one moves along the borehole M1. So we have two different electrodes. And here, these electrodes are connected to a voltmeter. So what we are doing here, we measured the change of the potential along the borehole wall with respect to a fixed point on the surface. And why it is interesting? Because if we measure the potential, so if just using the voltmeter that we have here, we measure the potential along the borehole, we see that in that case, we're going to see some change. For example, what you see here is the shale impermeable layer. And as you see, when we measure the potential along the shale layer, it almost tends to the positive side of the potential. And once we get to the in the front of the sandstone layer, the potential almost tends to the negative side of the potential. Okay. What I mean, if we draw a line here, so this line indeed corresponds to those layers that are impermeable. And whenever we see some deviation to the left of the to the left of the line, it corresponds to any permeable layer. For example, we may consider this layer as our permeable layer, and the other layers are impermeable. This is how it works. So it is very easy. Just for example, if we have like another situation like that, as I said, the positive side of the curve we consider as impermeable layers. So whenever we see some deviation, it means that we are able to identify our permeable layers. And here is impermeable, impermeable, and so on. So in order to explain how SP-like works, just let me explain the physics. So assume that we have a container and we divide the container in two halves. So as you see here in the middle of the container, we put or we place a permeable plate. So assume that we have like a sandstone plate we place in the middle of the container. What we do here in the right side of the container, we pour salty water or brine. On the left side of the container, we pour fresh water. Okay. So what happens? The salty water contains chloride sodium ions, and we know that ions tends to move from the area that the concentration is high to the area that the concentration is low. What what we what happens in reality is that chloride ions are much bigger compared to sodium ions, and as a result, they have much higher mobility. So chloride ions reach to the left side first, and as a result, because chloride ions have negative charge, what we're going to have here on the right side, we're going to have negative potential, and on the right side, because we have more sodium ions, we're going to have positive potential. Okay, this phenomenon is called liquid junction or diffusion potential. Now consider another scenario. In the second scenario, what we do, we place an impermeable layer in the middle of the container. So for example, we place a shale plate, and then again we pour the right side, we fill the right side with salty water and the left side with fresh water. And again, similar to the previous scenario, ions tends to move to the area with lower concentration from higher concentration. But here, what happens here, because here the layer is impermeable, the layer that we have put here is impermeable, the big chloride ions cannot move through the shell layer. However, some sodium ions, they can move because they are much smaller, so they can go through very, very tiny pores. So what happens if we measure the potential? Now we're going to notice that here the potential is positive here because in the front of this shell layer or in the vicinity of this shell layer, on the left side, we're going to have concentration of mm, positive sodium ions. Okay. And on the left side, we have more chloride ions. And that's the thing. Here, the potential becomes positive, and here, the potential becomes negative. And this phenomenon is called membrane potential. So just let me ask you a question, okay, in order to make sure that you understand this concept. Given the concept of liquid junction and membrane potential, if RW is smaller than RMF, so assume that the formation of the water formation is brine and mud filtered is fresh water, or drill mud is made from fresh water, what will be the spontaneous potential in the vicinity of an impermeable shale layer be a permeable sandstone layer? So now assume that here in the formation we have brine, doesn't matter if it is permeable or it's impermeable. Here we have shale. Here we have sandstone. What will be the potential in the vicinity of the shale layer? So assume that this is the borehole. So the answer is very, I think, easy. We should have positive ion in the front of the shale layer and negative ion in the front of sandstone layer. So the potential is positive in the front of shale and negative in the front of permeable sandstone. Now consider another situation here. Assume that in hypothetical, we're logging, we just deal with fresh water in the formation. It is not that usual for oil and gas exploration because usually oil and gas reservoirs are found in deep formations, few thousand feet below the surface. And in those depths, usually the formation water is bright. Now assume that in hypothetical um, scenario, we just deal with very, very near surface formation when the formation water is fresh water, and we have used brine to make our drill mud. Okay, so this is the situation. So what we're gonna have in the vicinity of shale layer, and here assume that we have sandstone. Here we have brine. In the borehole we have brine, and in the formation we have fresh water. So it is obvious that when we have here, we have brine, sodium ions will move into the shale layer. So in the vicinity of shale, we're going to have negative potential. And at the same time, here, we're going to have more chloride ion in the sandstone layer. So we're going to have more positive ion in the front of sandstone. So it's going to be a reverse situation. Okay, guys, something that you should notice here, in reality, because most of the times for formations are deep for oil and gas exploration, and at those depths, formation water is brine. So this is something that we should expect. If we have used, this is a very critical assumption. If we have used fresh water for our drill knot, in that case, we should always see positive potential for impermeable layers and negative potential for permeable layers. So this is something that you should consider. Now, just let me ask you another question. So what's going to be the spontaneous potential when we have oil-based drill mud? So this question is indeed is a little bit tricky. Okay. The answer of this question is that in that case, there will be no ion exchange between the mud filtrate and formation water because oil is not conductive. As a result, the spontaneous potential will not show anything. Okay. Okay, guys. So that's the major thing that you should consider. The spontaneous potential works only and only if there is a difference in the salinity of the formation of water and mud filtrate. Okay. So if the mud filtrate is fresh water, okay, in that case, we should see something in SP log. But assume that, for example, in some scenarios, for example, we have used brine, seawater to make our drill mud. In that case, if just we look at the spontaneous potential log, we don't see anything. So if, for example, you are in marine environment, the most accessible water is the seawater, and seawater is brine. In that case, definitely we're not going to get anything from spheroid because there is not that much difference in the salinity of the drill mud and also the salinity of mud filtrate and also formation water. Another point that I would like you to pay attention is that the SPLOI just shows if the layer is permeable or not, and it doesn't tell us anything about the permeability of the layer. Okay, just let me explain here better. So assume that this is the SPLOI that we deal with. So for example, what you see here, this is the like first impermeable layer, this layer, and this is another impermeable layer. So just impermeable, again, here is impermeable, and these two layers are permeable. So as you see, the second layer is more deviated to the left compared to the first layer, but because the deviation is higher doesn't mean that the second layer is more permeable. It can be related to the difference in the salinity of the formation. So, and that is correct. So whenever we see more deviation, we may interpret it as the formation water is more saline compared to another formation. So any deviation that we see uh, cannot be linked to permeability. Okay, that's something that you should notice. SPLog just tells us if the layer is permeable or not. Deviation to the left is not linked or doesn't correlate with the permeability of the layer. It mostly correlates with the salinity of the layer, the formation water. So here, just assume that we are given this data. So identify two permeable and two impermeable zones. So here is the answer. As I said, the area with positive potential, we can interpret it as impermeable. So the red zones are impermeable zone, and whenever we have deviation to the left, it means that we deal with permeable layers. Guys, one of the applications of SP log is to estimate RW, the resistivity of water in the formation, and why it is important Because if you remember, I said that according to Archie's law, if we have RW and if we measure RT, and if we have some estimate of the porosity in the formation, then we can estimate uh, water saturation in the formation and water saturation. If we have the water saturation, then we can estimate hydrocarbon saturation in the formation. And how we are able to do that? Because a spontaneous potential is linked to the temperature and also RMFE to RWE ratio. So what is SSP here? SSP is SP of permeable layer minus SP of impermeable layer. So for example, here the SP of impermeable layer is minus 58 and the SP of the permeable layer is 10. So SSP here is minus 58 minus 10 is equal to minus 68, so millivolt, 68 minus 68 millivolt. And here TD is the temperature at the formation, and RMF E is a parameter that is linked to RMF, and also RWE is a parameter that is linked to RW. So there is a chart, I'm going to explain it later, that we can use in order to calculate RMFE and RWE from RMF and RW values. Okay, so just we can rewrite the previous equation. So SSP is something that we can measure. TD, again, we can measure. And also we can measure RMFE. These are the things that we can measure. And if we do that, then using this equation, we are able to estimate RWE. And from RW, we can estimate RW. Here is the equation. RW is equal to RMFE 10 times 10 to the power of SSP over 61 plus 0.13 times TD. Okay, here is 10 to the power. Now just let me give you an example to see how we can, estimate RWE. Why you like currently using a simple calculator, we are able to estimate, use this equation to estimate RW. A simple calculator is enough, but just notice that in the past, the computer wasn't so accessible, and that's the reason companies develop some charts in order to do these calculations without need a computer or calculator. And here I'm going to teach you one of those graphical methods. And the reason why still we use these graphical methods, because we can use those cross plot charts in order to calculate different physical or petrophysical properties from our logging data. And because it is possible that you don't have access to software, because all of these things, we have different software applications that we can use in order to interpret and quantify the logging data. But I assume that you don't have access to the software. Still, you can use these graphical methods. Okay. So here I'm going to teach one of the graphical methods that how we can use them, use it in order to estimate RW. Okay, guys. So now I'm going to explain how, first of all, we measure RMF. So in the lab, it is easy to calculate RMF. So there are some filters to separate mud filtered from the mud. So assume that we have a sample of the real mud, and then in the lab, we separate the mud filtered using a filter, and then using the mud filtered sample that we have, we measure its resistivity. So we call that measure resistivity RMFM, or measure resistivity. And So here is something that you should notice, okay? The resistivity is a function of temperature, and the temperature in the lab is different from the temperature in the formation. So you have to correct that. So for that reason, you need two temperatures. So one of them is Tm, the measurement temperature in the lab, and also you need the temperature at the formation location. And if you do that, if you have that, then you can easily calculate the value of RMF at the formation location using this simple equation. Now here you may ask me a question how we can estimate TD, the temperature in the formation, and it is very easy. Usually when we have a logging operation, we have two different temperature measurement. We measure the temperature at the surface, or we call it ST, and also we measure the temperature at the bottom of the borehole. We call it BHD, the bottom of the borehole. And also we have the depth of the borehole is D. So if the depth of the formation is D, lowercase d, in that case, we are able to obtain TD here using this equation. So we have ST, that is the surface temperature. We have bottom of the borehole temperature. And here we have the depth of the borehole, capital D. We have the depth of formation. And using this equation, we can estimate TD. So this is how we measure TD. So we have surface temperature. We have bottom of the borehole temperature. You have the depth of the the borehole, the depth of the bottom of the borehole, that is capital D. And then we have the depth of the formation, that is lowercase d, and using this equation we can easily calculate that. So now consider this example. Assume that SSP is minus 68 millivolt. The temperature at the bottom of the borehole is 196 Fahrenheit. The depth of the borehole is 9,400 feet. And if we assume that here the surface temperature is 75 Fahrenheit and the depth of the formation is 4170 feet. In that case, assume that this is the temperature, this is the resistivity that we measure in the lab. So RMF measured in the lab is 0.71 ohm meter. So first of all, use this equation to calculate the temperature at the formation. And as you see here, the temperature is 129 Fahrenheit. And then we estimate the resistivity of RMF at the formation location, that is 0.39 ohm meter. And then now just consider that we want to measure RW. And as I mentioned before, just look at this equation. In order to calculate RW, we have to find RMFE to put it in the equation to calculate RWE. From RWE, we can estimate RW. So guys, we can use this chart to estimate the values of RWE or RMFE from the corresponding values of RW or RMF. And as you see, we on the horizontal axis, we have the values of RW or RMF, and on the vertical axis, we can find the values of RWE or RMFE. And what you see here we have some contours that correspond to the formation temperature. So in this example, the value of RMF was about 39 ohm meter, and we find that value and draw a line. So the temperature in the formation is about 129, so it lies between the contours of 100 degree, this is Fahrenheit, and also 150 Fahrenheit. By some interpolation, we find that the point and draw a line to cut the value of RMFE on the vertical axis. And if we do that, we notice that here is the value that we find for RMFE. So once we find RMFE, we can plug it in this equation. And here right now we have SSP, we have TD, and we have RMFE, and we can estimate RWE. And once we find RWE, again, we can refer to this chart to find RW. So the process is very simple. Now, instead of using that equation, you may use this graphical method. And this graphical method is very simple. So as you see, we have 4 stems. So the first stem, we have 4 stems. The first stem is a spontaneous potential stem. The second stem is RMFE over RWE ratio stem. The third stem is RMFE stem, and the fourth stem is RW stem. So just let me, and we have also a temperature bar here, and just let me tell you how it works. So the first thing that we do here, we find the value of RMFE on the stem 3, and then we find SSP value on stem 1, and then over the temperature bar, we find the temperature, and we draw a line. We draw a line that crosses these 2 points to cut stem 2. So over this bar, we find the value of RMFE over RWE, and we find the point, and there are another line that crosses these 2 points to cut the fourth stem. And over the fourth stem, we estimate, or we find the value of RWE, and then here the value of RWE is about 0.048 ohm meter. And then if we go to the chart, we find the value here, we draw a line, again we draw another line, and if we do that, we will find out that the value of RW is about 0.063 ohm meter. So this is the entire procedure. So instead of, if you're not happy or if you don't like mathematics, then you may use this graphical method. But I highly encourage you to use that equation because it is less prone to error. Okay, guys. So this is the summary of this lecture. So just let me summarize what you have learned in this lecture. The first thing, because the formations are deep, SPLOG works when we use fresh water to make our drill mud. Okay, so in the case that we use seawater or we use oil to make our drill mud, in that case, the SPLOG will not work. SPLOG shows positive potential when we have impermeable formation and negative potential when we have permeable formations. So for that reason, the interpretation is very straightforward. And also using SPLOG, we are able to estimate RW. And how the SPLOG works based on 2 potentials, diffusion potential and also membrane potential that I explained the physics. I hope that you have enjoyed this lecture, and see you again.